Hey there everybody, welcome to the second video on section 7.6. In this video we'll talk about what slope fields of systems with complex eigenvalues look like. It turns out that the slope fields of these kinds of systems look quite a bit different than slope fields of systems with only real eigenvalues. And if you think about it, it shouldn't take too much thought to figure out why that might be. Now that we've seen only real eigenvalues and complex eigenvalues, the real eigenvalue systems, recall from section 7.5, did not have trig anywhere in the answers. But in section 7.6, the complex eigenvalues somehow spit trig out in their answers. And so, of course, if you have functions with trig in them versus functions with no trig in them, right, you're going to get different behavior, different looking things. So anyway, let's just see what impact that trig has. Okay, so here is the system that we solved in the previous video. This was the motivating example. Here is its slope field. And again, this is a screenshot from your book. Your book makes all the arrows, all the little slope vectors have the same length, just to get an idea of the flow. If you want to use that GeoGebra tool that I sent you, here is the same slope field there. So there's just sort of more impact. The farther away from the origin you get, sort of the faster the flow is, whatever. So again, if all you care about is direction, though, it's just like a clockwise swirling around the origin. It looks like a hurricane or something, you know. So anyway, this kind of behavior, is suddenly now you get spiraling. We didn't see this kind of thing in section 7.5. There was no sort of spiraling, hurricane-y looking behavior. That's the effect that trig can have on these slope fields. That's the effect that complex eigenvalues can have. So now if I draw a phase portrait like this with trajectories in it, so again, recall what these are. These are pick your favorite start point and then follow the arrows. So if I pick a start point here and I follow the arrows, I go like, right? I get sucked into the origin, but I spiral in there, right? Any point that I pick will spiral like that into the origin. That's what the trajectories are doing. So if I pick a point down here like I did and you follow the arrows, you get sucked in like that. Okay, so again, not to belabor the point, not to repeat myself too much anyway, but these phase portraits and these slope fields all happen in x1, x2 space. So there's actually no time axis here. These trajectories are actually all parameterized curves over time, if you like that language. Anyway, so if you actually want a picture of x1, right? So again, this system, to solve it, means to figure out what both x1 and x2 are. So if you want graphs of those functions, then now you're talking about a space where t is the horizontal axis and either x1 or x2, depending on which one you care about, is on the vertical axis. Okay, so notice if you pick, let's see, pick any trajectory. Let's see which trajectories they've picked here. So one, I suppose, I'm not sure which ones they've picked. Anyway, so let's just think about picking this one here. So if I follow this and think about what happens to x1, what happens to x1? So remember, if you move left or right, that's what x1 is doing. So if you move left, x1 is going down. If you move right, x1 is going up. So I start by going to the left, means x1 is going down. So I guess if I follow this trajectory, it's kind of like following this plot of x1 here. Initially, x1 goes down. So I go down, but then right about here, I turn around and I start going to the right. Okay, so as I'm going to the right here, as long as I'm going to the right, x1 is increasing. So notice this curve, right, starts increasing. But then what happens here? I kind of turn around, don't I? So now I start going back to the left. So x1 starts going down. That's why this curve sort of starts going down. So again, following these trajectories around, if you want to know what x1 is doing, you just have to think about, as I follow this curve, am I going left or am I going right? If I'm going left, the function x1 is falling. If I'm going right, the function x1 is rising. And you can again do the same thing for x2. We talked about this in section 7.5. With x2 though, as you move up on this trajectory, x2 is actually increasing. Like it's just an up, up, and up. It's not up, down versus left, right. It's up, down versus up, down. Because x2 is this vertical axis. So if you want to get a picture of x2, then if you follow this trajectory, x2 is going up, 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 and then suddenly right here, x2 starts going down, 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 and down, but then right here, x2 turns around and goes up a little bit, right? So it's like up, down, up, down, up, down, but since you're spiraling into the origin, these curves are dying down. So in the limit, as t goes to infinity, both functions will limit to 0. So again, as we discussed with this example here, this is kind of like a spring mass system where there are two masses and they're moving in a damped medium, right, where damping is present, so that you jiggle them initially or something, right, but then over time the motion dies down for both masses. Okay, so let me just show you one more example. Let's think about this system here. So now that we know that whether you have complex eigenvalues or not can change sort of the qualitative behavior of your picture, you can get sort of spiraling like this, which we didn't see before, right? We got nodes before, or saddles before in the previous video. In nodes and saddles, there's no spiraling like this, right? The x1 plots did not have any waviness to them because there was no trig. Okay, so anyway, so here's a system where this alpha is left as a constant, but I'm not telling you what it is. So as you change alpha, you of course get a different system for every choice of alpha, therefore a different slope field. So if you put an alpha value of 2 in there, you get a different slope field, different system than if alpha is 13 or whatever. Okay, so is there a critical value of alpha at which the qualitative nature of the phase portrait changes? Or if you like, the qualitative behavior of the slope field, does that change? So to get an idea of this, just to play around, let me go back to my GeoGebra slope field guy, remind myself what the system is. So alpha is whatever. Let me just put it at 10 right now. That's what's going to change. 2y is fixed. I have negative 2x, and then I have 0y down below. Let me enter on this. Okay, so, well, it looks like that. Okay, whatever, right? And if I do a 12, it still kind of looks like that, right? So notice when you change from 10 to 12, the system is different, of course, right? But the qualitative nature hasn't changed. This appears to be sort of a node, like a repelling node. There's some sort of eigenvector here-ish, right? Like an eigenvector line here that's throwing things away from it. It's a repelling node or something. If I put like a negative 12 there, let's see what happens. Whoa. Back off of that. My goodness. Oh, it's not letting me clean that up. All right. Well, anyway, now it's sort of the opposite. Things are getting sucked in real quick to some sort of line like right in there, right? All the arrows are rushing towards there as fast as they can. All right, so that was a mistake to choose something like that. Let me choose a 6. Okay, with a 6, make it a little more dense. Again, you're seeing sort of like node-ish behavior. There's no sort of spiraling here, right? There's sort of some sort of line here, some sort of eigenvector line, which is sort of throwing things off of it. And then what if I put like a 5 there, whatever. Again, same kind of picture. So far, 5, 6, 10, 12, obviously the pictures are different, but the qualitative nature hasn't changed at all. This looks like a node-ish kind of picture from section 7.5. What if I put like a 2 there? Ah, this is different. This is swirling, you know? What if I put like a 1 right here? Swirling, right? So there seems to be some difference. There seems to be some sort of threshold, perhaps, right, between 1 and 2, and then the other set of values, right, between 5, 6, 10, 12, whatever the other ones I played with, right? So at some point, you pass from swirl to not swirl to node, right? Okay, so let's think about why that would be, and if we can think about what sort of like a critical value of alpha would be. Okay, well, we know now that complex eigenvalues versus real eigenvalues makes a difference, qualitative difference, in the nature of your slope field. So let's just think about what the eigenvalues of this matrix are. Well, you can ask Wolfram for that, right? You can hand Wolfram this 2x2 matrix. Wolfram, I don't know about an alpha, but you can put like an X or an R there or something, whatever, right? And just ask for the eigenvalues of that. And Wolfram will tell you this. Those are the eigenvalues of that matrix. Okay, so if you're thinking about the boundary between real and not real, right? What values of alpha would make this entire expression either real or not real? Well, real or not real is going to be determined by whether what's under the square root is positive or not. Okay, so notice when I put in things like, 5, right? 5 squared minus 16, I get something positive under the square root giving me something real. Same thing with 6, same thing with 10, same thing with 12. So any alpha value above 4, right? Any alpha value 4 or higher, I get a real set of eigenvalues. and therefore I won't get any spiraling. I'll get a notish sort of thing, or maybe a saddle, I don't know, right? But certainly not a spiral. However, if alpha is 2, now what's under the root is negative, and I get complex eigenvalues. So all that to say, alpha equal plus or minus 4. Those are like tipping points or thresholds, if you like. For any alpha value between those, you get complex eigenvalues. For any alpha outside of those, you're not going to get imaginary values, so you won't see any spiraling. So again, it's sort of interesting, nice, interesting, right? I mean, fascinating, I don't know what adjective, right? That thinking about these systems in terms of matrices lets you make observations like this, right? So again, if we hadn't thought about matrices at all, then this system versus the systems from 7.5, it might not be clear why their slope fields are looking so different. But because we took the time to learn some linear algebra, and we took the time to learn what, say, eigenvalues are, now we can just say these really nice little observations about these systems in terms of their eigenvalues. Like this system here, we expected swirling because the eigenvalues were complex, whereas in section 7.5, we did not expect this sort of spiraling because the eigenvalues were real. Okay, so after this, we're moving on to section 7.8. We notice we skipped some sections in chapter 7, right? Moving to 7.8, and in that question, or in that section, we will answer the question, what happens if you have eigenvalues that are repeated? So far, everything we've done, the eigenvalues are all distinct. You don't have an eigenvalue of 2 and then another eigenvalue of 2. So I want you to again notice the parallels to chapter 3. What did we do in chapter 3? Characteristic equation, right? And that was the flow of chapter 3. Real distinct roots. That was the first thing we dealt with. Then, distinct roots that might be complex. We did that next in section 3.3. Then in section 3.4, we moved on to repeated roots. What do you do then? So now in chapter 7, to finish this parallel narrative with chapter 3, we're going to finish chapter 7 by talking about what do you do with eigenvalues that are repeated.